Hello friends, welcome to my YouTube channel RF Design Basics. So in this video I will be explaining about the Routh-Hurwitz Criterion and we will do few examples based on this. So Routh-Hurwitz Criterion is very important criteria to check the stability of a closed loop control system. So first of all, we need to understand what is open loop transfer function in a control system and what is a closed loop transfer function. So if we have a system which is having GS as the gain of the system, GS, and then the system is having a feedback which is HS, and both are combined over here where the input is RS and the controlled output is CS. So we write CS by RS, CS by RS as the controlled output will be GS by 1 plus GS HS. So this is basically the closed loop transfer function. Closed loop transfer function. Here, if you just disconnect this system from here and you take output over this point, then the output will be GS into HS while the system is open. So open loop transfer function is GS, this is GS, and then it will be multiplied with HS. So basically there is a relationship between closed loop transfer function and open loop transfer function as closed loop transfer function is equal to GS, which is the gain of the system, divided by 1 plus open loop transfer function. So this is a very important relationship, and in this closed loop transfer function, to check the stability of this system, we need to write first the closed loop transfer function of the system, given system, and the denominator of the system, denominator. So denominator is basically this. Denominator of the system can be equated to 0 to find out the roots of the closed loop transfer function. So depending upon the roots, whether the roots of the system is in the left half of the S-plane. So if you have been given with the S-plane, so left half of the S-plane means the roots are negative, or the real part of roots, suppose the roots are over here, so the real part of the roots are negative. So if there is positive value of real part of the roots, in that case the system is unstable. So this region is basically unstable and this region is stable, and we have a imaginary line over here. This imaginary line is marginally stable, means if there is little bit change, it may be in the unstable zone. That's why it is called marginally stable. So to determine the instability or stability of the system, we need to find out the denominator of closed loop transfer function, and then we will try to find out if there is any roots existing in the right side of S-plane. So this is a rough idea of Routh-Hurwitz criterion. So basically what we do is we will take the function and then we will try to understand. Let us say you have been given with a characteristic equation SQ plus 4.5 S square plus 3.5 S plus 1.5 equal to 0. Let's say this is characteristic equation. Characteristic equations are those equations which is derived by taking denominator of a closed loop transfer function equal to 0. So when closed loop transfer function denominator equal to 0, you will be able to find out the characteristic equation. So the method is you have SQ, S square, S and the constant. So just write SQ, S square, then S to the power 1 and finally S to the power 0. So it should be written in the decreasing order. Then all the SQ and S, these constant you can write in the first row, that is 1, constant here is 1, here it is 3.5. Then you can take the S square and the constant term. So alternative you have to choose. So here it will become 4.5 and then 1.5. After that we have to do the calculation. So first one is calculating like this, 4.5 into 3.5. Then we will be calculating this way. So this 4.5 into 3.5 will be, we can write 4.5 multiplied by 3.5 minus 1 into 1.5, that is 1.5, divided by this 4.5. And then if we have further any numbers, then we can do the same thing with the first column itself. But there is nothing, so next will be 0. If you calculate this, you will get roughly 3.16. This is still in the first column, 3.16 in the first column only. Now this first column, this 3.16 multiplied by 1.5 divided by 3.16. So here you will do 3.16 multiplied by 1.5, then minus 4.5 into 0, that is 0, divided by 3.16, which will be 1.5, still in the first column. Second column is 0. Now we have to just check the first column if there is any sign change. So this is positive 1, positive 4.5, positive 3.16 and positive 1.5. So while coming from top to down, there is no sign change. No sign change. So if there is no sign change, means the system is stable. We'll take another example. In that we might be having some sign change. So let us take that one. Consider a system whose characteristic equation is S5 plus 1.5 S to the power 4 plus 2SQ plus 4S square plus 5S plus 10 equal to 0. So this is characteristic equation. So we are going to write S5, S4, S cube, S square, S1 and S0. And let's see the values of S5. Then we'll be writing, after S5 we'll be taking SQ constant, then S constant. So alternative we have to write. So here we can write 1, then 2, then 5. There is nothing after that. And then here this is 1.5. So first 1.5, then for S square it is 4, and for constant it's just 10. Now I'll do the calculation. 1.5 multiplied by 2 is 3, 3 minus 4 is 1, and divided by 1.5. So it's 1.5, 3 minus 4 divided by 1.5. This is roughly negative value 0.66. So that is first column. Now second column, we have to take 1.5 multiplied by 5, that is 7.5 minus 10. So it is 2.5 divided by 1.5, it's coming minus 1.66. So you have to always start from this to any column. So first we have started 1.5 into 2, so that is 3, and then 1 into 4, so 4, 3 minus 4 divided by this number. Same thing we will do with 5, 10 also. So 1.5 into 5, 10 into 1, so divide by 1.5, that will get minus 1.6. Now we will take this 0.66 and will multiply with 4, because this is my next number. So here, rather writing here, we should write minus 1.66 here. So 0.66 into 4 and 1.5, 1.66. So if you do that, you will get 0.227. And here, if I multiply with 0.66 into 10 and then 0 divided by same minus 0.66, so you will get this number 10. So whenever you don't have the third column, this column, then obviously that will be 10, this value directly. Then from here we will be multiplying this with minus 1.6 and 0.66 with 10. So you will get 27.4, and here we will get 0. Then next it will be this number 10 and 0. So what you will notice is there is 2 sign change. From where? Only for first column we have to check the sign change. Is there any sign change? No. Positive, positive. From here to here, positive to negative. So here we will write 1 sign change. Here 0 sign change. From here to here, when we are moving, then we can see there is again 1 sign change, because negative to positive it is becoming. So 1 more sign change. After that it is positive and positive. So 0 sign change. So total we have 2 sign change. That's why this system is unstable. So we'll take few special cases in our next example. So this example contains a special case which is very important. Let's write that. It is the characteristic equation directly I am writing S5 plus S4 plus 2SQ plus 2S square plus 11S plus 10 equal to 0. So S5, S4, S3, S2, S1, S0. Start from here 1, 2, 11. So 1, 2, 11. Then 1, 2, 10. So 1, 2, 10. Let's write the values. 1 into 2, 1 into 2. So 2 minus 2 divided by 1 is 0. So the value is 0 over here. So that is becoming a special case. Whenever we get first column as 0, that will automatically become a special case, because we'll come to know that. 1 into 11, 1 into 10. So 1 divided by 1. So it will be 1. This is 0. So there is nothing after this. Here you can see, because of this 0, if I want to write the next row, there is a problem, because I want to write next row means 0 into 2 minus 1. So that is 0 minus 1 divided by 0. So divided by 0 is not possible. That's why whenever you come across 0 in the first column, just assume that quantity as very small. Let's say this epsilon is very small and it tends to 0. That is your assumption. Now write the next expression using this epsilon. So 2 epsilon minus 1 divided by epsilon. So it will become 2 into epsilon minus 1 divided by epsilon. Then second number. Second number will be 0 into 10. So epsilon into 10. So 10 epsilon divided by epsilon. And next will be 0. Now from here we'll take this one, 2 epsilon minus 1 divided by epsilon into 1, and then we will multiply with this and we'll get the we'll divide by this. So we can write that as 2 epsilon minus 1 divided by epsilon we have taken, multiplied by 1, then minus epsilon, 10 epsilon by epsilon. So it is basically epsilon and epsilon cancel, so it is 10. So 10 epsilon divided by this 2 epsilon minus 1 by epsilon. So this is a large number. Then here it will be 0. So next number is 0. Now if I want to write next number, it will become by default 10. Why it is 10? Because some quantity multiplied by 10 divided by this quantity. So obviously you will end up getting 10. Now apply this epsilon tends to 0 for each of the column, and I will write those values in the bracket. So obviously this will remain 0. So this value is 0. Here if I put epsilon tends to 0, this is 0 minus 1 by 0, which is roughly minus infinity. This value is minus infinity. And if I put here epsilon tends to 0, we can actually solve this. It will become 2 epsilon 1, 2 epsilon minus 1, then minus 10 epsilon square and divided by 2 epsilon minus 1. So if I just do the calculation and epsilon tends to 0, so this will give me a value which is 1. If I just put epsilon tends to 0, so if I apply everywhere, it will be epsilon 0, this is minus 1 divided by minus 1, it is plus 1. So we have found the remaining values in this column, and now we can see the sign change. So from here there is no sign change, it is 1 1. Here 1 to 0, no sign change. Here 0 to minus infinity, so it is becoming minus infinity, so there is 1 sign change. Now from here to here it's again 1, so minus infinity to 1, so there is 1 sign change, and then it is 10, it's 0 sign change. So totally you have 2 sign changes. If there is even 1 sign change, then it will be unstable system. So this system is unstable because there are 2 sign changes of the roots. Now this sign changes may be possible due to this kind of cases wherever you get 0 in first column, not the entire row. If you just get 0 in first column, it means that there are 2 equal and opposite real roots. Or one more case is that there are 2 purely imaginary roots. So if there is purely imaginary roots, that means those roots are on the middle vertical line. So those cases will be marginally stable provided the first column is having no sign change. So if 0 has come without any sign change in the first column, then that is called, that will be roughly marginally stable. So next, one more problem I'll show you here, which is again the special case where we have to write the auxiliary equation. So let's see, if I take S6 plus S5 plus 5s to the power 4 plus 3s cube plus 2s square minus 4s minus 8 equal to 0. This is our characteristic equation. Always remember, this is not our denominator of open loop transfer function. Rather, this is denominator of a closed loop transfer function. And let's write the S6, S5, S4, S3, S2, S1, S0. And write alternative values. So alternative values I am just highlighting. Here we can write 1, then 5, 2, and minus 8. Then we can write 1, 3, 1, 3, minus 4, and 0. Now we'll just multiply 1 into 5, 5 minus 3, 2, 2 divided by 1. So multiplication like this. 5 minus 3 divided by this quantity. So 1, that means 2. 5 minus 3 is 2, divided by 1 is 2. Then 1 into 2 minus plus 4, 6 divided by 1. So this is 6. Then 1 into minus 8. So minus 8 minus 0 divided by 1. So it's minus 8. Then 2 into 3. 6 minus 6, it is 0. And 2 into minus 4, minus 8 minus plus 8, again 0. Then next is 0. So here we get a problem. The entire row has become entire row is 0. Entire row 0. So previously we have seen the special case where just first term is 0. Here the entire row is 0. So for this kind of cases we have to write the auxiliary equation. So whenever we come across the entire 0 terms, we just go back to the previous row and write the auxiliary equation by taking this as S4, then this as S square. So here this is S4, so we will be writing S4 for this, then this will be S square, and this will be a constant. So just keep on reducing. So it will be 2 into S4, then 6 S square. So plus 6 S square minus 8. So this is basically auxiliary equation. So AS is 2S square plus 6S square minus 8. What we do is we take differentiation dAs upon ds. So this will be 8s cube plus 12s minus 0. Now we will take the constant term of this and use it for the next row. So we have taken auxiliary equation of this row. Now we'll just change this 0, 0, 0 with these values. So we'll just write in the bracket, this value is basically should be 8 and this should be 12, and this is by default 0, and we'll also mark as star because here we have used the auxiliary equation condition and then we have found the constant value. Now we'll again multiply 8 into 6, 48 minus 24 divided by 8. So it's 3. Then 8 into minus 8, minus 2 into 0, so this you will get minus 8 and then 0. Now again 3 into 12, 36 plus 64, 100 divided by 3. And then 3 into 0, it's 0. You multiply this, you will get this number over here. So now see the sign change. No sign change. No sign change. From 2 to 8, no sign change. From 8 to 3, no sign change. No sign change. And there is one sign change over here, because from positive it is becoming negative. So this system is unstable. So this was the special case where we have one row having entire term as 0. Now we'll take one more special case where two rows will become 0, and then we will see how that kind of system is not stable. Let us take characteristic equation as Fs equal to S6 plus 3S5 plus 6S4 plus 12S plus 12S square plus 12S plus 8 equal to 0. And now I will write this as S6, S5, S4, S3, S2, S1 and S0. Start from S6, then this, then this and then this. So the values are 1, 6, 12, 8. Then we have 3, then 12 and 12. 3, 12, 12. Just multiply. 3 into 6, 18. 18 minus 12, 6 divided by 3 is 2. 36 minus 12 by 3, so 24 by 3, 8. Then 3 into 8, 24 minus 0 by 3 is 8. Here itself we will get 0, 0, 0. 12 into 2, 24 minus 24, 0. 2 into 12, 24 minus 24, 0. So we have got 0, 0 over here. This is obviously 0 by default. So this is now we have to write a characteristic equation over here because entire term is 0 in a row. So go to the row before that and write that expression as characteristic equation As equal to 2s to the power 4 plus 8s square plus 8. Take differentiation. ds by ds, this should be 4 8s cube. So this term is basically 8. Now let us calculate again for the next term. 8 into 8 is 64 minus 32. 64 minus 32 is 32 divided by 8. Divided by 8 is 4. Then 8 into 8, 64 minus 0 by 8, that is 8. So 4 and 8. Now multiply 16 and 4. 64 minus 64, 0. 4 into 0, anyway 0. So again we are getting 0. So we have to go back and write the auxiliary equation for this. So write it. 4, this is now auxiliary equation. Second auxiliary equation is 4 as a square plus 8. So take the differentiation. dA dash s by ds. This will become 8, 4 into 2, 8s. That's all. So for this term we should have 8 over here. So this is going to be the second one, the second row with entirely 0. If you get this kind of case, again we multiply. 8 into 8 is 64 divided by 8 is 8. So what we can see is there is no sign change from top to bottom. 1, 3, 2, 8, 4, 8, 8. Everything is positive. But there are two rows with zeros. That means there is repetition of imaginary roots. For example, if you have suppose s is something like plus minus 3j, so there are two roots with same value, means s equal to plus minus 3j again. Basically if you have s equal to plus minus 3j, it means that s square plus 3 equal to 0. So if I take a square of this, that means repetition of root is there. So if there is repetition of root of imaginary values, then definitely the system will become unstable. So this system is unstable and it is of a special case where two of the rows becomes 0 and there is no sign change. If sign change is there, definitely the system is unstable. But even if sign change is not there and you get 2 zeros rows, then it will be unstable system. I hope I have covered all the special types of functions for Routh-Hurwitz criteria. Thank you.